Hello and welcome to the 181 video on binary linear classification. Today we'll be talking about a new type of problem, and that's displayed over here in blue. Let's say that we have a bunch of data points, each data point representing a person. In blue are people who have a certain disease, and in pink are people who don't have that disease. We also have a bunch of information about these people. We may have things like their genetic markers, their smoking habits, their exercise habits, etc., etc. And our problem is, given a new person, we want to be able to predict based on that information that we know about them if they're likely to have the disease or not. So in sort of spirit of linear regression, the first thing that we might do is maybe we know certain things like genetic markers make the disease more likely and exercise makes the disease less likely, and there's some sort of overall likelihood if we knew nothing about a person, W naught, that we would predict this is sort of how likely they are to have the disease. And so we can put that all together sort of in a linear formula. So we'll have our W naught, and then we'll add some coefficient times the genetic marker because we think that makes the disease more likely. And then we'll subtract some coefficient times how much they exercise in hours per day or something like that because we think that makes the disease less likely. And as a notational aside, similarly to linear regression, if we write the x's as a vector starting with 1, and that's the same one as we used in the bias trick, and then genetic marker, exercise, etc., all the other data categories and dimensions that we have. And then we write W as W naught, W1, which is a coefficient for genetic marker, W2, which is a coefficient for exercise, etc., etc. Then we can actually just write this linear combination as WTXN, which is both notationally convenient and also makes it easier to see some derivatives later. So why don't we just go ahead and do this? For xn, for some data point, xn, we'll predict WTXN, and then we'll find the optimal W using our loss function. The same thing from linear regression. This will be great because we've already solved this problem, so we won't need to do any more math, and we know there's an analytic solution. It's very clean. Well, there are a number of issues with this approach, but the biggest one is that it penalizes strong signal. So let's say somebody is really likely to have the disease based on the information that we know about them, then the value WTXN is probably going to be much, much greater than 1. And usually in our categorical variable, yn, we have it equal to 1 if somebody has the disease and -1 if they don't have the disease. And so the problem with this is that this will be counted as a loss term. If we predict something greater than 1, then this squared term for that data point is actually going to be greater than 0. So that'll actually exert pressure to push down the coefficients. Same thing will happen if somebody is really, really unlikely to have the disease. So you sort of get coefficients that are not accurately representing things because you're counting over predictions in the correct direction as a loss, which is not what we want to do. So to address this problem, we're going to augment our approach a little bit. Now, we're going to consider h of x given w. We're going to define that function as WTX, the dot product of w and x. So that's our linear predictor from our previous discussion. And we're going to actually predict 1 if this is greater than or equal to 0, and -1 if this is less than 0. And this will help ameliorate our issue because if we have a data point such that WTXN is really, really big, well, we'll just predict 1, which is what we want to predict in that case. And we'll also change our loss function. So we'll use a 0-1 loss. And what that means is for every data point, we will add 1, and when you see 1 here, this is an indicator random variable. So that means that if this thing in the parentheses is true, it's equal to 1. Otherwise, it's equal to 0. So we're going to add 1 to the loss if our prediction is not equal to the true value of that data point. And otherwise, we'll add 0. We won't do anything. So our overall loss is just the number of points that we misclassify. And that seems like a really good metric because a W where we don't misclassify any points is probably better than a W where we misclassify 1 or 2 or 3 points. And they just get worse the more points that you misclassify. So now we have we've solved the issue of our loss function not really reflecting what we want it to actually reflect. And we're unfortunately going to still run into an issue here, and that will be in the process of trying to find the optimal W. So usually to find the optimal W, we'll take the gradient of W and we'll either set that to 0, or in our last video we talked about gradient descent, so even if we can't analytically solve it or the problem's not convex, we can just move in the direction of the negative gradient and eventually get there. But this all requires having a gradient for W, and we don't really have a good gradient for W. So let's say we have these data points here, and just say that W is two-dimensional for now, And we'll just focus on changing the intercept of W right now to make it really simple. So that just corresponds to, right, shifting the line up and down. And let's say it's correctly classified these points, it's correctly classified these points, but this point right here is misclassified. So we want some sort of technique that will eventually increase our intercept so that we correctly classify that point. Well, the problem is that as we increase the intercept, until we've actually increased the intercept right past this point, it's not going to actually change the loss at all, right? Because you can increase from this first red line to this second red line, and you're going to still misclassify the exact same number of points. So your loss function is not going to change at all. I've drawn the loss function below. It's going to be exactly 1 until you get to the intercept that correctly classifies this point right here. And then now the loss is going to be 0. But the problem is, 1, we're not really going to be able to analytically solve this loss very well. And 2, the gradient is not going to point us in the right direction. The gradient at basically every point in this function is just 0. So we can't move in the negative gradient direction to move towards what we want to classify. So we need to change the loss function once again. So we'll use the same linear predictor, but now we're going to change our loss function a little bit. And the key idea here is that the loss under line 1 here should be more than the loss under line 2 here. And that means that when we take the negative gradient, we move in that direction, it'll start to move us towards a more correct decision boundary. So that's how we want to change our loss function. So we're going to use a formula called ReLU, which is rectified linear utility. And ReLU is just equal to, ReLU of z is equal to 0, the maximum of 0 and z. So in other words, if z is negative, it's just equal to 0, and if z is positive, then it's equal to z. So it's a pretty simple function, but it's going to help us a lot here. Now, we're going to take the ReLU of negative, the dot product of wt and x, and yn. So the absolute value of yn is always going to be equal to 1, right? Because it's equal to 1 if the person has the disease and negative 1 if they don't. So really what we're doing here is if yn and our predictor have the same sign, so in our last model, right, that would correspond to a correct prediction. So if they have the same sign, then then this inside the ReLU, negative h of xn given w times yn will be negative, so that'll just be 0. So if we correctly classify it, then there's no loss. And for the data points that we misclassify, that means that yn has the opposite sign of h xn given w, and so then it'll be negative, and then you multiply by this negative in front, and you get a positive quantity, so that will positively contribute to the loss. So now we see that basically our loss is sort of a count of how many things we've misclassified, but for each point we've misclassified, we're adding w, t, xn. And this is a little bit better because now we can actually take the gradient. We'll talk about the specific mathematics of doing the actual gradient in the mathematics section, but you'll see that now line 1 has a higher loss than line 2 because under line 2 the misclassified point is a little bit closer, and so that means that the gradient will eventually push us towards the actually correct decision boundary. So you might be wondering, why do we choose to use ReLU instead of a linear function? Just like a linear function would just be, we take negative yn times h of xn given w, right? This would still be positive when we correctly classify a point, or positive when we incorrectly classify a point, and negative when we correctly classify a point. So in fact, it would even reward us for correctly classifying points. And also, it's a little bit weird because here we think that if our misclassified point is further from the decision boundary, then we consider it a worse error, but we don't consider it better if our correctly classified points are farther from the decision boundary, right? So if we do a really good job predicting our correct points, then we're not rewarded any more than if they're really close to the decision boundary. But we do make this distinction for misclassified points. So it seems like it would be more consistent to use a linear function here. Well, the problem is that adding rewards this function, right, adding negatives to the loss, for correctly classified points means that the algorithm might prefer to actually just classify certain things really well and incorrectly classify other things, but the benefits of classifying certain things quote unquote really well, having them be really far on the correct side of the decision boundary, will outweigh the benefits of correctly classifying all the points. And our overall goal is to get a decision boundary that classifies all the points correctly. So to illustrate this below, let's say that we have one class in green and another class in red. A good boundary might be something like this in the middle, but under a linear loss function, our boundary might be something over here, or actually it would just go infinitely in this direction because it would be getting positive, or it would be getting negative contributions to the loss from these 2 points and only taking a little bit of added loss from this point. And so it would just be incentivized to put a completely nonsensical decision boundary in this case. So ReLU is actually helpful here. And we'll also see that there are some theoretical guarantees, but this is basically an illustration of some why those theoretical guarantees hold more for a ReLU. So the last thing that I want to say before we hit the math is that basis transformations can allow for nonlinear boundaries. So as we discussed in the linear regression video briefly, if you have this sort of linear formula of WTXN, then this defines like a hyperplane. And so any data that's like linearly separable by a hyperplane, we can separate with this methodology, but we can actually separate other stuff. And we can do this through basis transformations. So here phi of x is just like some function on x, and then so you can think about it as just doing some sorts of basis transformations. So maybe now maybe phi of x will be defined as 1 and then x0 squared, but it could also be something like x1 plus x2 squared minus x3 or something like that. So any sort of functions, and that will allow us to draw nonlinear boundaries, something like this, and be able to classify different types of points. So now let's move on to the math. So again, remember, I've just copied down our loss function from above. So the first thing that we want to do is take the gradient of the loss function. And since it's a sum, we can just take the gradient of every element of the sum. And so the correctly classified points will be somewhere like here on the 0 part of the ReLU curve. And the derivative or the gradient with respect to W is just going to be 0, right? Because the gradient is just a vector of derivatives where you take derivative with respect to W0, derivative with respect to W1, and you put that in a vector. And if you infinitesimally change any of those W's, it's just going to change the prediction a tiny bit, but it's still going to be the correct prediction. So the ReLU of the prediction will still be 0. So you're not actually changing the value of that part of the sum. So those won't contribute to the gradient at all. The things that will contribute to the gradient are the terms, the non-zero terms. So if you misclassify a point, then your contribution will be this to the loss, and the gradient of this with respect to W is just negative xn yn. And you can, that's one by matrix rules, or two, you could just think about sort of what is the gradient. The gradient is the vector of all the derivatives, and the derivative of, so WT xn just equals W naught plus W, we'll write it as W naught x naught, x naught plus W1 x1, etc., etc., etc. So partial WT xn, that's partial W of WT xn equals first the derivative with respect to W0, which is just x0, then the derivative with respect to W1, which is just x1, all the way down. And so this just equals the x vector, and then yn is just some scalar that you're multiplying by, and so is negative 1. So that's how it comes out if you want to see all the mathematical details of that. So anyways, we sum up the non-zero terms of the gradient, and thus we get for every yi that's not equal to yi hat, we're using yi hat here. This is the same thing as the yi hat is just the predicted value of yi. So it would just yi hat is equal to 1, or negative 1 is equal to 1 if h of x comma w is greater than or equal to 1, and else it's equal to negative 1. So if we misclassify the point because the prediction is not equal to the true value, then we sum over all those points the gradient of those values, which is the negative xn times yn. So if you sum that here, we're just summing that up for all the points that we misclassified. So now, since we have a gradient of w, we could try saying that equal to 0, but w doesn't actually contribute to the gradient, so that's not going to give us a solution for w. So we'll use our numerical technique of gradient descent that we discussed in the last video. The first way we can do it is, this is just a formula for gradient descent. So you take a w at a certain time step, and then you subtract the negative learning rate times the gradient, and that gives you your next w. So here we just plug in the gradient, and we get this. Now, we'll often do, as we talked about stochastic gradient descent, we can just pick a random subset of the data. And in fact, one way you can do stochastic gradient descent is just with one data point. And so there's an algorithm called perceptron, which is actually guaranteed to find the linearly separable boundary for the data if it exists. And it is just stochastic gradient descent. So instead of taking the gradient over all the points, we'll just pick some random I, and then we'll take the gradient for those points. So this sort of supposes that I is such that yi is not equal to yi bar, but that's a fair assumption to make, because if I is such that yi equals yi bar, like if we correctly predict it, then this implies that the gradient of the loss just over that point is equal to 0, so it doesn't actually do anything, so we can just skip that step. So we can just randomly sample from the i's that we misclassify, and then update according to that gradient, which will be xi, yi, and this is the formula for stochastic gradient update. So we'll see that if we do that, that will actually converge to the correct linear boundary, which is the theoretical guarantee that I was referring to earlier. So that's one way to solve binary linear classification problems, and hopefully walking through what you might think to do and why those things don't work helps a little bit better understand why we've chosen the approach that we have.